Now in this lecture we'll find out the radius of the big circle. In the drawing we have a big triangle. Inside the big triangle we have two circles and one square. The side length of this square is equal to 3 units. The radius of the small circle is equal to 1 unit. And our mission is to find out the radius of this big circle. Okay, so first of all, we define the vertex of the triangle as A. We define this vertex as B. We define this vertex as C. We define the point of tendency of tangent BC with the small circle as D. We define the center of the small circle as O, and we define the center of the big circle as P. We define the point of tendency of tangent BC with this circle as Q. We define the point of tendency of the square with the circle as E. We define the touching point between side AC and the vertex of the square as F. We define the touching point between this side of the square and side BC as H, and we define the touching point between this side of the square and side BC as L. We define the point of tendency of the circle with side edge F as M. We join points O and M together by a straight line. So here point O is the center of the circle. Point M is the point of the circle itself. Therefore, OM is the radius of the small circle that is equal to R. And R equals to 1 unit. Here we have the radius OM that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees. And this angle will be also equal to 90 degrees according to rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. Likewise, we have the radius OD that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we have the radius PQ of the big circle that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We know that all the angles inside the square are right angles, so this angle will be equal to 90 degrees. This angle will be also equal to 90 degrees. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Side EF equals to 3 units, side LH equals to 3 units. And we have also here rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So here, side BC of triangle ABC is the side of a triangle. It is absolutely a straight line. So if we focus on the upper side of the straight line BC at point L, the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of BC at point L? We have this angle that is equal to 90 degrees plus this, the missing angle. In total, they must be equal to 180 degrees. Therefore, this angle must be equal also to 90 degrees. In order to complete the sum of the angles on the upper side of BC at point L to 180 degrees, this angle must be equal to 90 degrees. Likewise, if we focus on the upper side of BC at point H, the sum of the angles in point H must be equal to 180 degrees. So which angles we have here? This angle is 90 degrees. Therefore, the missing angle must be equal to 90 degrees, exactly like here. Okay, so actually we found out that in quadrilateral MOHD, in this small quadrilateral, we have 1, 2, 3 right angles. So therefore the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So in order to complete the sum of the angles here to 360 degrees, this angle must be equal to 90 degrees. So here in quadrilateral MOHP we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral MOHD as a rectangle. Why? Because it has 4 right angles. Okay, quadrilateral MOHD is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, MO equals to HD. MO equals to HD. MO equals to HD according to the rule that the opposite sides of a rectangle are equal to each other. But here, according to what we only found out, we only found out that MO equals to 1. So we can write here MO equals to 1, and from this equation 1 equals to MO equals to HD, we will derive that HD is also equals to 1. HD equals to 1. We can write here that HD equals to 1. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that OD equals to MH. OD equals to MH. But here, OD equals to 1. It is the radius of the small circle. And from this equation, 1 equals to OD equals to MH, we will derive that MH is also equals to 1 unit. Here, MH is equal to 1 unit. MH equals to 1 unit. MH equals to 1 unit. So here, FH is one side of square EFLH, therefore it is equal to 3 units. MH equals to 1, therefore FM will be equal to 3 minus 1, that is 2. So here we will define the point of tendency of tangent AC with the big circle as K. And I will present to you rule number 2. We will define the point of tendency of tangent FC with the small circle as N. In the next step, I will present to you rule number 2. according to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB, and according to this rule number 2, they are equal to each other. That is to say, PA is equal to PB. You can implement rule number 2 in our drawing. Why? Because in our drawing, we have the common external point, point F. From the common external point, point F, we have two tangents to the small circle, tangent Fn and tangent Fm. And according to rule number 2, they are equal to each other. That is to say, Fm equals to Fn. Fm equals to Fn. But Fm equals to 2 units, therefore Fn must be also equal to 2 units, because they are equal to each other. Likewise, according to rule number 2, if we focus on the common external point, point C, for the common external point, point C, we have two tangents to this small circle, tangent Cn and tangent CD, and according to rule number 2, they are equal to each other. So, if we define tangent CD as x, then tangent Cn must be also equal to x because of the fact that they are equal to each other according to rule number 2. Okay, so in the next step, we will implement the Pythagoras theorem on the right green triangle FHC. On the right green triangle FHC, here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, the hypotenuse of the green right triangle is FC, therefore the square of the hypotenuse is FC squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to FH squared plus HC squared. Repeat again, according to the Pythagoras theorem, on the right, in the right green triangle FHC, FC squared equals to FH squared plus HC squared. So here, what is the value of FC? From the drawing, it is very easy to see that FC is equal to 2 plus x. Here, again, FC equals to 2 plus x, therefore FC squared equals to 2 plus x squared. And it is equal to FH squared. FH equals to 2 plus 1, that is 3. Therefore, FH squared will be equal to 3 squared, that is 9, plus HG squared. What is the value of HC? It is very easy to see from the drawing that HC equals to 1 plus x, or x plus 1. So, HC equals to x plus 1, therefore HC squared will be equal to x plus 1 squared. So, in conclusion, we found out that according to equation number 1, 2 plus x squared equals to 9 plus x plus 1 squared. Here we will open the brackets on both sides of this equation number 1, and we will get that according to equation number 1, 2 plus x squared equals to 2 squared, that is 4, plus x squared, plus 2 times 2x, that is 4x. And it is equal to 9 plus x plus 1 squared equals to x squared plus 1 squared, that is 1, plus 2x. So here we have x squared on both sides of this equation number 1, so x squared will get cancelled. So what is left of equation number 1 after we cancelled x squared? In this side of the equation we have 4 plus 4x. And the other side of this equation, equation number 1, we have 9 plus 1 is 10 plus 2x. So here we subtract 2x from this equation, equation number 1, and we get that according to equation number 1, 4x 4x minus 2x is 2x. So here we will have 4 plus 2x that is equal to 10 is equal to 10. So here we subtract 4 from this equation, equation number 1, and we get that according to equation number 1, 2x equals to 10 minus 4 is 6. Here we will divide this equation, equation number 1 by 2, and we will get that x, according to equation number 1, x equals to 6 over 2 is 3. So x equals to 3 units according to equation number 1. So we can write here that x equals to 3 units. X equals to 3 units. And here also x equals to 3 units. Okay, so in the next step, we'll join points O and then together by a straight line. Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of the small circle that is equal to 1. So R equals to 1 unit. We have the radius ON that is 1 to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. In the next step, we'll join point C and O together by a straight line. By joining point C and O by a straight line, we created here two right triangles, triangle OCN and triangle ODC. In the next step, we will prove that those two right small green triangles can go into each other according to side rule. So here, triangle NOC is congruent to this triangle, triangle ODC. So why those two green small triangles can go into each other? First of all, NO equals to OD. They are both the radii of the circle, therefore they are equal to each other. NO equals to OD. They are both the radii of the circle, that is equal to 1. In addition, NC or CN equals to CD according to rule number 2. CN equals to CD, they are both equal to 3 units according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. It's a common side that belongs to both triangles. So actually we proved that the two green small right triangles can go into each other according to side rule. So I write it down, triangle NOC can go into triangle DOC according to side rule. And for the fact that the two right angles can go into each other, we derive that those two angles are also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles must be also equal to each other. So if we define one angle as theta, if this angle equals to theta, then this angle must be also equal to theta because of the fact that those two angles are equal to each other. Okay, in the next step we join points N and D together by a straight line. When joining points N and D together by a straight line, we created here triangle NDC. Okay, and according to what we did until now, we can conclude that CO is the angle bisector of angle C. I repeat again, CO is the angle bisector of angle C. So write it down. Line segment CO is the angle bisector of angle C. Why? Because it bisects angle C into two halves. Each half equals to theta. In triangle NDC. This triangle NDC. I'll repeat again. We actually found out that CO is the angle bisector of angle C, triangle NDC. In the next step, we join points K and P together by a straight line. Point P is the center of the circle, point K is the point of the circle itself, therefore PK is the radius of the big circle that is equal to R. In the next step, we join points C and P together by a straight line. By joining points C and P together by a straight line, we created here two big right triangles. The right triangle KPC and the right big triangle PQC. We will prove that those two right triangles can congruent to each other according to side rule. Here KP equals to PQ, KP equals to PQ. They are both the radii of the big circle that is equal to R, therefore they are equal to each other. Triangle KPC, triangle PQC. In addition, if we focus on the common external point C, from the common external point C, we have two tangents to the big circle, tangent CK and tangent CQ. Tangent CK and tangent CQ, and according to rule number 2, they are equal to each other. That is to say, CK equals to CQ. CK equals to CQ according to rule number 2. And finally, CP is the common side that belongs to both triangles, so CP equals to itself. CP equals to itself. It's a common side that belongs to both triangles. So we actually proved that the two big right triangles can go into each other according to side rule. So I write it down. We proved that the right big triangle KPC is congruent to the right big triangle PQC according to side rule. And from the fact that the two right big triangles can go into each other, we will derive that those two angles are equal to each other. According to the rule that corresponding angles congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta. In the next step, we join points K and Q together by a straight line. By joining points P and K and Q together by a straight line, we created here triangle KQC. And according to what we did until now, we can conclude that CP is also the angle bisector of C. So I write it down. CP is the angle bisector of angle C in triangle KQC. Repeat again. We found out that CP is the angle bisector of angle C in triangle KQC. Again, CP is the angle bisector of angle C in triangle KQC. So, in conclusion, we found out that angle C is two angle bisector. Angle bisector OC and the angle bisector BC. And actually, we know CO, but we will prove that CO passes through point P. So our claim is that the angle bisector CO passes through point P. Okay. CO passes for point C. Repeat again. Now I claim that CO passes for point C. Here. The angle bisector CO passes for point C, or in other words, points point C, O, and P, they are all located on the same straight line. So we will prove this claim in a negative way. Okay. So here, in a negative way, we will assume that CO doesn't pass for point P. Okay, I'll repeat again. We'll assume that CO doesn't pass for point P. Here, CO doesn't pass for point P. So according to our assumption, we have here two angles, angle D DCO or angle DCO equals to theta. So we have, according to our assumption, this angle DCO, it is equal to theta. And it is very easy to see from the drawing that the leg DC of the angle is part of BC. Here, DC is part of BC. So if DC is part of BC, it means that DC and BC are located on the same straight line. Okay? Because of the fact that here DC and BC are actually, or DC is part of BC, it means that DC and BC are located on the same straight line. So I write the conclusion that DC and BC, they are both located on the same straight line. And what about the second leg of this angle? I will first of all draw the second angle PCB. We have the second leg and the second angle, that is angle PCB. This is the big angle PCB. So this is the second angle PCB. So I already mentioned before, BC and DC, both legs are located on the same straight line. What about the second leg of those two angles? What about the legs OC and PC? You see in the drawing, we have leg CO and leg CP. Okay, if CO doesn't pass through point P, it means that CO and CP are located on two different straight lines. Okay, if CO doesn't pass through point P, it means that CO and CP, they are located on different straight lines. Okay, the only way that CO and CP are located on the same straight line, then they will be located on the same straight line only if CO passes through point P. Otherwise, they are located on different straight lines. But according to our assumption, CO doesn't pass for point P. Therefore, CO and CP are located on different straight lines. Okay? So can write down that the second leg of the two angles, that is to say CO and CP, are located on different straight lines. This is according to our assumption. So if we have two angles, that one leg of the two angles are located on the same straight line and the other angle is not located on the same straight line, it means that there must be different angles. They can never be equal to each other. When one leg is located on the same straight line, then in order that the two angles will be equal to each other, the second leg must be also located on the same straight line. But according to our assumption, the second leg is not located on the same straight line because of the fact that CO doesn't pass for point P. Therefore, those two angles are two different angles. So if this angle is theta, this angle must be angle alpha, and alpha is not equal to theta. Okay, so we actually found out that angle C has two different angle bisectors. That bisected into two different halves, into two different halves, while here, while the angle bisector CO bisect angle C into two halves, theta, theta, and theta, the second angle bisector PC bisects angle C into two halves that are equal to alpha and alpha. And this is not possible. Why it is not possible? Because if, for example, angle C equals to 30 degrees, then any angle bisector of angle C must bisect it in two halves, that each half equals to 15 degrees, and 15 degrees only, and not to any other halves. Okay? But according to our conclusion, angle bisector angle C is two different angle bisectors. So due to the contradiction, that is to say that angle bisector C is two different angle bisectors that bisect it into two different halves, we will conclude that our assumption that CO doesn't pass through point P is not correct. Therefore, CO must pass for point P. So to summarize the proof, we proved this claim that CO passes through point P in a negative way. We assumed that CO doesn't pass through point P, then we arrived to the contradiction, and due to the contradiction, we must conclude that CO indeed passed through point P. We finish with the proof. In the next step, we will focus on triangle ODC. In triangle ODC, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle, triangle PQC, this angle equals to 90 degrees, this angle equals to theta, therefore this angle must be equal to 90 degrees minus theta, for the same reason that this angle also equals to 90 degrees minus theta. In the next step, we will prove that the big right triangle PQC is similar to the small right green triangle, triangle NODC. Okay, so I write it down. We will prove that the big right triangle, triangle PQC, is similar to the small green right triangle, triangle ODC. So why those two triangles are similar to each other? First of all, we just right now found out that those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So here, angle QPC, the big right triangle, is equal to this angle, that is actually angle DOC, the small green right triangle. Repeat again, angle QPC, the big right triangle, equals to angle DOC, the small right green triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. Okay, so this angle is angle PQC, and is equal to this right angle, that's angle ODC. And again, angle PQC in the big right triangle equals to angle ODC in the green small right triangle. They are both equal to 90 degrees, therefore they are equal to each other. And finally, we have this angle, angle theta is a common angle, so angle theta equals to itself. So we can call angle theta as angle PCQ. Angle theta equals to itself, so we can call to angle theta also angle DCOCD. So here we call to angle theta two different names, and we state that angle theta equals to itself. It's a common angle that belongs to both triangles. So in conclusion, we actually proved that the big right triangle PQC is similar to the small green triangle ODC according to angle similarity rule. So I write it down, triangle PQC is similar to triangle ODC according to angle similarity rule. Okay. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PQ in the big right triangle over OD in the small green right triangle is equal to QC in the big right triangle over DC. So I write it down. We conclude that PQ over OD is equal to QC over DC. Repeat again, and we conclude that PQ over OD equals to QC over DC. So here PQ equals to R, OD is the radius of the small circle that is equal to 1, over QC. What is the value of QC? The value of QC equals to, here we have 3 plus 1 is 4 and 4 plus 3 is 7. So it is 7 plus QL. So we substitute QC by 7 plus QL over DC. What is the value of DC? Here DC equals to X, that is equal to 3 units. So we substitute DC by 3 and we get that according to equation number 1, R equals to 7 plus QL over 3. Here we multiply this equation number 1 by 3 and we get that according to equation number 1, 3R equals to QL plus 7. Here we subtract 7 from this equation number 1 and we get that according to equation number 1, QL is equals to QL equals to 3R minus 7. So I found out that according to equation number 1, QL is equals to 3R minus 7. So I can write here that QL is equals to 3R minus 7. Because of the fact that the side depth of this square is equal to 3 units, we will examine 3 cases for the value of R. Either R could be less than 3 units, R could be equal to 3 units exactly, and R could be greater than 3 units. So we examine each case. We start with the first case. Case 1. What happens if R is less than 3 units. Okay, if the radius of the big circle is less than 3 units. So here I will draw a circle that its radius is less than 3 units. The side length of the square is 3 units, therefore it will be higher than the radius. So here here the radius R is drawn to the point of tendency, therefore this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. So inside quadrilateral PL Q P PM QL, inside this quadrilateral we have 1, 2, 3 right angles. Again, inside this quadrilateral PMQL we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral PQML is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say that in rectangle PMQL, side PM must be equal to side QL. Yes, side PM equals to QL. But here PM equals to R, so we can write here that PM equals to R. And from this equation we derive that R equals to PM equals to QL, we derive that R equals to QL. Okay, so from one side QL equals to R. From the other side, QL equals to 3R minus 7. So from this equation, R equals to QL equals to 3R minus 7, we will derive that R equals to 3R minus 7. Here, we subtract R from this equation and we get that 0 equals to 3R minus R is 2R minus 7. We will add 7 to this equation and we will get that 2R equals to 7. We divide this equation by 2 and we get that R equals to 3.5 units. R equals to 3.5 units. But according to our assumption, R is less than 3 units. So we have here a contradiction. R cannot be simultaneously less than 3 units and also equals to 3.5 units. So we have a contradiction, therefore we cancel this possibility. R cannot be less than 3 units. So we have the second possibility that R equals to exactly 3 units. So case 2 is that R equals to 3 units exactly. So if R equals to 3 units, then you will have a circle that is radius equals to exactly 3 units. So we draw a circle with a radius of 3 units. The radius of this circle is equal to 3 units. R equals to 3. And the side length of the square is also equals to 3 units. Here, this angle equals to 90 degrees according to rule number 1. So inside quadrilateral PNQL, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So quadrilateral PNQL, that has 4 right angles, will be a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, Pn is equal to QL. But according to our assumption, R equals to 3, so we can write down that Pn is equal to R equals to 3. So here, from this equation, 3 equals to Pn equals to QL, we will derive that QL is equal to 3. So from one side, QL equals to 3 units, from the other side, QL equals to 3R minus 7 according to what we have already found out. So from this equation, 3 equals to QL equals to 3R minus 7, we will derive that 3 equals to 3R minus 7. So here, we will add 7 to this equation, and we will get that 3 plus 7 is 10, so 10 equals to 3R. We will divide this equation by 3, and we will get that R equals to 3 and a third. R equals to 3 and a third, while according to our assumption, R equals to 3. So it is a contradiction. R cannot be both equal to 3 and 3 and a third. Therefore, due to the contradiction, we cancel the second case. R cannot be equal to 3. So we left only in the third possibility that R is greater than 3 units. So case number 3 is that we examine the case number 3, that R is greater than 3 units. So here we draw a circle with a radius that is greater than 3 units. And because of the fact that the side length of the sphere is 3, it will be shorter than the radius. So here we have points E and F, E, F, H, F. Here from point E we draw perpendicular on the radius PQ. I repeat again, from point E we draw perpendicular on the radius PQ. So this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and PQ as T. So actually inside quadrilateral PEQL, this quadrilateral, we have 1, 2, 3 right angles. Okay? Therefore, the fourth angle must be also equal to 90 degrees. This angle must be also equal to 90 degrees. So inside quadrilateral PEQL, we have 4 right angles. Therefore, quadrilateral PEQL is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, here PE, PE, actually here it is side TE. Side TE, this side is side TE. Must be equal to side QL. According to the rule that the opposite sides of a rectangle are equal to each other. T equals to QL, but we already found out that QL equals to 3R minus 7. So from this equation T equals to QL equals to 3R minus 7, we derive that TE is also equals to 3R minus 7. Okay, TE is also equals to 3R minus 7. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that side TQ of the rectangle must be equal to side EL. But here EL is one side of the square that is equal to 3 units, and from this equation TQ equals to EL equals to 3, we'll derive that TQ is also equals to 3 units. Here TQ is equals to 3 units. So what is the length of PT? PT is very easy to see from the drawing that PT is equal to PQ minus TQ. Repeat again, PT equals to PQ minus TQ. So PT is equals to PQ, that is the radius of this circle, that is R, minus TQ, that is 3. So in conclusion, we found out that TP equals to R minus 3. So in the next, we'll join points P and D together by a straight line. By joining points P and D together by a straight line, we created here a right triangle, but here point P is the center of the circle, point E is the point on the circle itself, therefore P is the radius of the circle, that is equal to R. So here we have the right triangle, triangle PET. I will copy the right triangle, triangle PET in a new page, and we will implement the Pythagoras theorem on the right green triangle, triangle PET. Okay. The hypotenuse P equals to R. Here, PT equals to R minus 3. And T equals to 3R minus 7. So actually, this is the right triangle, triangle PTE that I copied from the original drawing. Now we will implement the Pythagoras theorem on this right triangle, triangle PTE. So here, by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the square of the hypotenuse is PE square, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to PT square plus TE square. So here PT equals P equals to R, therefore PE square is R square, and it is equal to PT square. PT is R minus 3, therefore PT square is R minus 3 square plus TE square. TE is 3R minus 7, therefore TE square is 3R minus 7 square. Here we'll open the brackets on this side of this equation, equation number 1, and we'll get that according to equation number 1, R square is equal to R minus 3 square is R square plus 3 square, that is 9, minus 2 times R times 3 is minus 6R, plus 3R minus 7 square is 3R square, that is 9R square, plus 7 square, that is 49, minus 2 times 3R is minus 6R, and minus 6R times 7 is minus 42R. So here we have R square on both sides of the equation, so R square will get cancelled. What is left from the equation number 1 after we cancelled R square? In this side of the equation nothing is left, we have 0. In the other side of the equation we have left with 9R square minus 6R minus 42R is minus 48R, plus 9 plus 49 is 58. So in conclusion, we got that quadratic equation that 9R square minus 48R plus 58 equals to 0. and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for, and we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, the coefficient a equals to 9, the coefficient b equals to minus 48, and the coefficient c equals to 56. And the variable that we are looking for in our specific quadratic equation is r, so x equals to r. So here we put the data inside the equation for x, and we get that x equals to r, so r equals to minus b, b equals to minus 48, so minus b is minus 48, it is plus 48, plus minus square root of b squared. B is minus 48, so minus 48 squared is 2304, minus 4 times AC. Minus 4 times A is 9, so minus 4 times 9 is minus 46, and times C is 56, so minus 48 times 56 is 2088. All divided by 2A, A is 9, so 2A is 18. So here we found out actually that R equals to 48 plus minus 2304 minus 2088 is 216, so inside the root we have to leave 216 over 18. So here we have R equals to 48 plus minus the square root of 216 is 14.6969 over 18. So here we have two solutions that are possible for R. The first solution for R is that R equals to 48 minus 14.6969 over 18. So here R equals to 48 minus 14.6969 is 33.3031 over 18. 33.3031 over 18 is 1.85. So R equals to 1.85 according to the first solution. But we already found out that R cannot be less than 3 units, and 1.85 is less than 3 units, therefore we cancel this solution, and we're left only with the second solution, that R equals to 48 plus 14.6969 over 18. So 48 plus 14.6969 is 62.6969 over 18 will give us that R equals to 3.483 units. So we found out that the radius of the big circle equals to 3.483 units. Okay, so in the next step I'll summarize the lecture. Actually, in the drawing we have a big triangle. Inside this big triangle we have two circles and a square. The side length of the square is equal to 3 units in its length, and the radius of the small circle is equal to 1 unit. And our mission is to find out the radius of the big circle. Okay? So, first of all, I will present to you the 3 rules that we used in order to solve this question. Okay? The first rule is that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. We have here tangent AB, that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is drawn to the point of tendency. Therefore, whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have two tangents to this circle. We have tangent PA and tangent PB, and according to rule number 2, they are equal to each other. That is to say, PA equals to PB. Then I presented to you rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So we have here the straight line CD. So if we focus on the upper side of the straight line CD at point O, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of CD at point O? We have angle alpha and angle beta, and according to this rule number 3, alpha plus beta must be equal to 180 degrees. So we use these 3 rules all over the solution of this question. So here we focused on the small quadrilateral MOHD. According to the 3 rules that I mentioned, we actually arrived to the conclusion that this small quadrilateral MOHD is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, MO equals to HD. MO equals to HD. But we know that MO is the radius of the circle that is equal to 1. So we can write here MO equals to 1, and from this equation 1 equals to MO equals to HD. We will derive that HD is also equals to 1. Here HD equals to 1. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we can get that OD is equal to MH. OD equals to MH. But here OD is the radius of the circle that is equal to 1. So here from this equation 1 equals to OD equals to MH, we derive that MH is also equals to 1. So we actually found out that quadrilateral OMHD is not a rectangle but a square. Then we actually here we have used here rule number 2 from the common external point. Here we know that this is MH equals to 1 and FH equals to 3. So FH, that is 3 minus MH, that is 1. 3 minus 1 is 2. So FM equals to 2. Then we use the rule number 2. According to rule number 2, if we focus on the common external point F, from the common external point F, we have two tangents to the circle, tangent Fn and tangent Fm. And according to rule number 2, they are equal to each other. That is to say, Fm equals to Fn. But Fm equals to 2, therefore Fn must be also equal to 2. Likewise, we focus on the common extent point C. From the common extent point C, we have two tangents to the circle, tangent CD and tangent Cn. And according to rule number 2, they are equal to each other. That is to say, Cn equals to CD. So if Cn equals to x, then CD must be also equal to x, because they are equal to each other. Then we implemented the Pythagoras theorem on this right green triangle FHC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, FC square equals to FH square plus HC square. Again, in the right triangle FHC, FC square equals to FH square plus HC square. Here, FC, what is the value of FC? The value of the hypotenuse FC equals to 2 plus x. Therefore, FC square is 2 plus x square, and it is equal to FH square. FH equals to 3, therefore FH square is 3 square, that is 9. What is the value of plus HC square? What is the value of HC? HC equals to 1 plus x, therefore HC square equals to 1 plus x square. So in conclusion, found out that according to equation number 1, 2 plus x square equals to 9 plus x plus 1 square. Here we open the brackets on both sides of this equation number 1, and we get that according to equation number 1, 2 plus x square equals to 2 squared, that is 4, plus x square plus 2 times 2x, that is 4x, and it is equal to 9 plus x plus 1 square. X plus 1 square equals to x square plus 1 plus 2x. Here we have x square on both sides of equation number 1, so x square will get cancelled. What is left of equation number 1 after we cancel x square? What is left here is that in this side of the equation we have 4 plus 4x, in the other side of the equation we have 9 plus 1, that is 10 plus 2x. So here we subtracted 2x from this equation number 1, and we found out that according to equation number 1, 4x minus 2x is 2x, so in this side of the equation we left only with 4 plus 2x, and the other side of the equation 2x plus 2x is 0, so we left only with 10. So here we have 4 plus 2x equals to 10. We subtracted 4 from this equation number 1, and found out that according to equation number 1, 4 minus 4 is 0, so in this side of the equation we have 2x. In the other side of the equation we have 10 minus 4 is 6. So in conclusion, we found out that 2x equals to 6. We divided this equation number 1 by 2, and we got that x equals to 6 over 2, that is 3. So here x equals to 3 units, and here also x equals to 3 units. Then we added points O and N together by a straight line. Point O is the center of the circle. Point N is the point of the circle itself, therefore ON is the radius of the circle, that is equal to 1 unit. Then we joined point C and O together by a straight line, and this way we created two right green triangles, and we proved that those two green right triangles can go into each other according to side rule. Here, why they can go into each other? First of all, we know that NO equals to OD, they are both the other of the circle, therefore they are equal to each other. In addition, CN equals to CD, they are both equal to 3 according to rule number 2. And finally, CO is the common side that belongs to both triangles, so CO equals to itself. So actually, both the two green small right triangles can go into each other according to side rule. Okay, then we join points N and D together, in this way we create triangle NDC. Okay, we can conclude from what we did until now that CO is the angle bisector of angle C. Why? Because it bisects angle C into two halves, each half equals to theta. So here, CO is the angle bisector of angle C in triangle NDC. Then we join points P and K together by a straight line. Point P is the center of the circle, point K is the point of the circle itself, therefore PK is the radius of the circle, that is equal to R. Then we prove that those two big right triangles, triangle PKC and triangle PQC, can go into each other according to side rule. Why they can go into each other? First of all, KP equals to PK, they are both the other of the circle, therefore they are equal to each other. In addition, If you focus on the current start point C, from the current start point C, we have two tendencies to the second. Tendency K and tendency Q, and according to rule number 2, they are equal to each other. So CK equals to CQ, and finally CP is the current side that belongs to both triangles. So CP equals to itself. So we actually proved that the two big right triangles can go into each other according to side rule. Okay? And here those two big right triangles can go into each other according to side rule. So we join points K and Q together by straight line. In this way, you create a triangle KQC. We can conclude from what we did until now that CP is also the angle bisector of angle C. It bisects angle C into two halves. Each half equals to but before that, because of the fact that those two triangles can go into each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two angles must be also equal to each other. So if one angle is theta, then the other angle is also theta. But we already found out that, so here we can write down that CP is the angle bisector of angle C, triangle KQC. And we have already found out that CO is also the angle bisector of angle C in triangle NDC. I'll repeat again, those two triangles, the small green triangles can go into each other, therefore those two angles are equal to each other. So if one angle is theta, then the other angle must be also equal to theta. So we actually found out that angle C has two angle bisectors. Angle bisector CO and angle bisector CP. And then we proved that CO passes for point P. Our claim is that CO passes for point C. Here, CO, the angle bisector CO passes for point P. Or in other words, points C, O, and P, they are all located on the same straight line. So we proved this claim by a negative way. We actually assumed that CO doesn't pass for point P. We arrived to a contradiction, therefore we must conclude that our assumption is not correct, and therefore CO must pass for point P. And that is the process of the proof. Okay, so according to our assumption, in a negative way, CO doesn't pass for point P. If CO doesn't pass for point P, we'll have here two angles. We have angle OCD that is equal to theta, and it is very easy to see that CD is part of BC. Again, CD is part of BC. If CD is part of BC, it means that CD and BC, they are both located on the same straight line. So we can write here that CD and BC, they are all located on the same straight line. CD and BC, they are both located on the same straight line. Then I copied the second angle that we have here. The second angle is angle PCB. This angle PCB. So this is angle PCB, and BC is located on the same straight line of CD. So they have a common leg. Why? Because those two legs are located on the same straight line. So you can see it as a common leg. Okay, what about the second leg? The second leg is PC here in this angle, and this OC in this angle. The second leg, here, leg OC and leg PC. according to our assumption, CO doesn't pass through point P. If CO doesn't pass through point C, it means that CO, point C, O, and P are not located on the same straight line. If points C, O, and P are not located on the same straight line, it means that they must be on different straight lines. Actually, CO will be on the straight line of CP, on the same straight line of CP, only if CO and P are located on the same straight line. But if CO doesn't pass through point P, it means that those two, CO and CP, are not they are located on this different straight lines. Otherwise, CO will pass from point P. So therefore, we can conclude from this fact, according to our assumption, that CP and CO are located on different straight lines, and when we have one angle that is one leg that is a common leg, and the second leg of the two angles are not located on the same straight line, it means that those two angles cannot be equal to each other, because when you have one leg of the two angles that is located on the same straight line, then the other leg must be also located on the same straight line in order that the two angles will be equal to each other. Otherwise, those two angles cannot be equal to each other. But according to our assumption, CO doesn't pass through point C, therefore those two legs are located, that is to say, CO and PC are located on different straight lines, and therefore those two angles are different angles. They can never be equal to each other. So if this angle is theta, this angle is alpha, and alpha is not equal to theta. So we actually found out that angle C has two different angle bisectors that bisects it into two different halves, while the angle bisector CO bisects angle C into two halves that each half equals to theta, that is to say bisect it to theta and theta. Then angle bisector PC bisects it into two different halves that each half equals to alpha, so it is bisected to alpha and alpha. And this is actually, it is not possible. Why it is not possible? Because if angle C, for example, equals to 30 degrees, then any angle bisector will bisect angle C into two halves that each half equals to 15 degrees. So it will be bisected by any angle bisector into 15 degrees and 15 degrees, and not to any other halves. So here we have a contradiction, and because of the contradiction we must conclude that our assumption that CO doesn't pass through point P is not correct. Therefore we conclude that CO passes for point P. Yes, CO passes for point P. Then we focus on triangle, the right green triangle ODC. This angle equals to theta, this angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus 90 degrees is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. So if you focus on triangle PQC, we have this angle is theta, this angle is 90 degrees, therefore this angle must be equal to 90 degrees. So then we prove that triangle PQC is similar to triangle ODC. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, Angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. So actually we found out that the two right triangles are similar to each other according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that PQ over OD equals to QC over DC. Again, PQ over OD equals to QC over DC. PQ equals to R, OD is 1 unit, it is the radius of the small circle. QC, what is the value of QC? QC equals to 3 plus 1 plus 3, that is 7, plus QL. So we substituted QC by 7 plus QL, and finally DC equals to 3 units. So in conclusion, found out that according to equation number 1, R equals to 7 plus QL over 3. Here we multiply this equation and equation number 1 by 3, and found out that 3R equals to QL plus 7. We subtracted 7 from this equation, equation number 1, and found out that QL equals to 3R minus 7. Here we can find out that QL equals to 3R minus 7. Then, because of the fact that the side length of the square is equal to 3 units, we examined 3 possibilities for the value of this circle, the big circle. So the radius of the big circle can be less than 3 units, it can be equal to 3 units exactly, and it will be greater than 3 units. So we examined each case. We have the first case that R is less than 3 units. So if R is less than 3 units, then we'll get this drawing here. Because of the fact that R is less than 3 units, then the radius will be shorter than the side length of the square that is equal to 3 units. So here, the side length of this square is longer than the radius. According to rule number 1, the radius here is drawn to the point of tendency, therefore this angle will be equal to 90 degrees. So inside quadrangle PM and Q we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So quadrangle PMQL is a rectangle because it has 2 right angles. As we know that the opposite sides of a rectangle are equal to each other. That is to say, here P is actually this, the point of tendency, we define it as point T. So therefore PT will be equal to QL. Okay, PT equals to QL, but PT equals to R. It is the radius of the big circle. Okay, and so from this equation, R equals to PT equals to QL, we derive that QL is also equals to R. QL is also equals to R. Here QL equals to R. So from one side QL equals to R. From the other side QL equals to 3R minus 7. So from this equation R equals to QL equals to 3R minus 7. We derive that R equals to 3R minus 7. So we subtracted R from this equation and we got that R minus R is 0. 3R minus R is 2R. So we got that 0 equals to 2R minus 7. We added 7 to this equation and found out that 2R equals to 7. Here we divided this equation by 2 and found out that R equals to 3.5 units. So found out that the radius of this big circle equals to 3.5 units. But according to our assumption, the radius of this circle is less than 3 units. So R cannot be both less than 3 units and also equal to 3.5 units. It is a contradiction. Due to the contradiction, you can say the first case, R cannot be less than 3 units. Then we examine the second case. What happens if the radius of this big circle is equal to exactly 3 units? So if the radius is equal to 3 units, it means that we will have here a circle with a radius that is equal to 3 units. And also the side length from the square is equal to 3 units. So we will have the same height to the radius and the side length from the square. So this is the point of tendency, therefore according to number 1 this angle equals to 90 degrees. So here in quadrilateral P, N and Q, 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral P, N, Q, L we have 4 right angles, therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say Pn equals to Ql. But Pn is the radius of the circle that is equal to R, that is equal to 3 units. R equals to 3 units. So we get here that 3 equals to Pn equals to Ql. From this equation we derive that Ql is also equals to 3 units. So for one side Ql equals to 3. From the other side we have already found out that Ql equals to 3R minus 7. So from this equation 3 equals to Ql equals to 3R minus 7, we will derive that 3 equals to 3R minus 7. Here we subtracted, we added 7 to this equation and found out that according to this equation 3 plus 7 is 10, and so 3 equals to 10 equals to 3R. So here we divided this equation by 3 and found out that the radius of this circle is equal to 3 and a third. 3 and a third. So, but according to our assumption, the radius of this circle is equal to 3. So the radius of this circle cannot be simultaneously equal to 3 and 3 and a third. Due to the contradiction, we cancel this possibility. R cannot be equal to 3 units. So, therefore, examine the third case. If R is greater than 3 units, then we will have this drawing. You can see here that the radius here is higher than the square. Okay? Because R is greater than 3 units. Again, here from point E, from this point E, we draw perpendicular on the radius PQ. Again, from point E, we draw perpendicular on the radius PQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. In this way, we created quadrilateral ETQL that has 1, 2, 3 right angles. Therefore, 1, 2, 3 right angles. Okay, those two angles are equal to 90 degrees according to what we have already found out. This angle equals to 90 degrees according to our construction. So we have 3 right angles, therefore the fourth angle must be also equal to 90 degrees. In quadrilateral ETQL, the fourth angle must be also equal to 90 degrees, therefore quadrilateral PEQL is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, TE is equal to QL. TE equals to QL. But we have already found out that QL equals to 3R minus 7. So we can write here that QL equals to 3R minus 7. And from this equation, TE equals to QL equals to 3R minus 7. We will derive that TE is also equals to 3R minus 7. Here, TE equals to 3R minus 7. Likewise, according to the rule that the opposite sides of rectangle TE E, Q, L are equal to each other, we get that here TQ is equal to EL. TQ is equal to EL. But here EL is the side length of the square that is equal to 3 units. EL equals to 3. So from this equation TQ equals to EL equals to 3, we will derive that TQ is also equals to 3 units. Here TQ equals to 3 units. What is the value of PT? From the domain it is very easy to see that PT equals to PQ minus TQ. Again, PT equals to PQ minus TQ. So PT equals to PQ, that is R, minus TQ, that is 3. So in conclusion, we found out that PT equals to R minus 3. Then I copied the right triangle PTE in the new page and implemented the Pythagoras theorem on this right green triangle. So this is the right green triangle that I copied from the original drawing. We implemented the Pythagoras theorem on this green right triangle. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PE square equals to PT square plus TE square. Again, PE square equals to PT square plus TE square. PE is R, so PE square is R square plus PT square. PT is R minus 3, therefore PT square is R minus 3 square plus TE square. TE is 3R minus 7, therefore TE square is 3R minus 7 square. Here we open the brackets on this side of equation number 1 and we found out that according to equation number 1, R equals to R minus 3 square. R minus 3 square equals to R square plus 3 square, that is 9, minus 2 times R times 3 is minus 6R, plus 3R minus 7, 3R minus 7 square is equals to 3R square, that is 9R square, plus 7 square, that is 49, minus 2 times 3R is minus 6R, times 7 is minus 42R. So here we have R square on both sides of the equation, so R square will get cancelled. So here, what is left after we cancel R square? We have 0 equals to, here we have 9 plus 49 is 58, and minus 42R minus 6R is minus 48R, and we have here also 9R square. So in conclusion, we have the quadratic equation that 0 equals to 9R square minus 48R plus 58. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So in our specific quadratic equation, the coefficient A is equal to 9. The coefficient B equals to minus 48, and the coefficient C equals to 56. And the variable that we are looking for is R, so x equals to R. So we put the data inside the formula for x, and found out that x equals to R, so R equals to minus B. B equals to minus 48, so minus B is minus 48, that is plus 48, plus minus b square. B is minus 48, so b square is minus 48 square, that is 2304. Minus 4 times a is 9, so minus 4 times 9 is minus 36, and minus 36 times c is 56. So minus 36 times 56 is 2088 over 2a. A is 9, so 2a is 18. So in conclusion, found out that the radius of the big circle is equal to 48 plus minus 2304 minus 2088 is 216. So inside this root we have left only with 216 over 18. So here we have the square root of 216 is 14.6969. So here we have two solutions that are possible for R. So R equals to 48 plus minus 14.6969 over 18. the first solution for R is R equals to 48 minus 14.6969 over 18. 48 minus 14.6969 is 33.3031 over 18. And 33.3031 over 18 is 1.85. So according to the first solution, we found out that the radius of the big circle capital R is equal to 1.85. But we have already found out that the radius of the big circle cannot be less than 3 units. And 1.85 is less than 3 units. Therefore we cancel the solution and we left only with the second solution, that the radius of the big circle equals to 48 plus 14.6969 over 18. 48 plus 14.6969 is 62.6969 over 18. And 62.6969 over 18 is equal to 3.4883 units. So in conclusion, we found out that the radius of this big circle is equal to 3.483 units. So here we found out that the radius of the big circle is greater than 3 units, and according to our analysis, it is absolutely possible that the radius is greater than 3 units. Okay? In conclusion, we found out that the radius of this big circle is equal to 3.483 units. Okay? Thank you very much.